So in 1926 something like that, this Compton proposed when photon incident and electron some atom. Okay, electrons, we know electrons revolve around the nucleus. This photon make collision with electrons. Because of this collision, this photon lost some energy to this electron, and electron will go one direction or it will recoil in one direction, and photon will also scatter in different direction. Okay, after that, after scattering this photon, the change in the energy or change in the energy or wavelength or frequency, whatever you can say. Instant is incident wavelength is lambda I, suppose if you take, and after scattering the photon wavelength is lambda f, suppose final wavelength and initial wavelength. The difference is they found h by m naught c into 1 minus cos theta. Okay, cos, that is the shift between incident and scattered photon. Okay, so here we will see this is the E proposed, E calculated the shift in the photon instant and scattered. Okay, that is the Compton shift. Okay, so now we'll see here. So this is the, here you can see in this image. Okay, here incident photon is coming and hit the nucleus or atom, and the photon, same photon is came. Okay, this is, it is coherent scattering. Coherent scattering means photon is not losing any of energy. Okay, any of this energy. But if you see Compton effect, Compton scattering, or here see, photon is hitting some electron and electron going one direction and photon going another direction. This is the Compton scattering. Okay, you can see coherent means the photon is not losing any energy to any electron. Okay, so here I will show you some animation, you will be clear now. So here photon, this photon means here incident photon coming yellow color. Can you, what, any doubt? You can see animation, isn't it? Can you see animation?
Yes, sir.
Yes,
Yes,
sir.
sir.
So
Yes.
yellow color is the some incident photon. Okay. Once this is the nucleus and electrons are fixed or revolve around the nucleus. Okay. Once this photon hit the electron, so electron, this this heart electron is going one direction. You can see after that the photon color also changed. That is red, right? So that indicating after making collision, the photon losing energy to electron. Okay, because of some energy gaining this electron, this electron getting kinetic energy going some other direction. Okay, so here this is also collision, also elastic collision. Elastic means, okay, before collision, after collision, energy is conserved and also momentum also conserved. Okay, that is the, so that is the elastic collision. Inelastic means energy will not conserve. Okay, either energy or momentum. Here see what Compton proposed, or what Compton discovered, or what Compton derived the expression. So incident photon having some frequency or wavelength or some energy. Okay, right? That is lambda incident photon, or lambda I, you can say lambda I. After hitting this photon, incident photon losing some energy to this electron, so that this electron gaining some kinetic energy and this electron moving some other direction, and after hitting, after collision, this photon also moving another direction. Okay, by losing some energy. Okay, that is why incident photon wavelength is lambda, and final photon wavelength is lambda dash or lambda f, you can say. The difference between incident and scattered photon wavelength is given by h by m naught c into 1 minus cos theta. Theta is the angle, how much it is scattered from the initial path, that is the scattering angle. Okay, this is the scattering effect. After that, okay, this is the counter scattering effect. Okay, is this clear now? What, how it is changing? Okay, now I will explain clear. Is it clear, everyone? Counter scattering means,
Yes, sir.
just suppose
Yes,
Yes,
sir.
sir.
take simple
Yes, sir.
example. You are going on bike. Okay, suppose you are going on bike, you hit suppose in front of you one person is going. Okay, if you hit that person will go one direction and you also go other direction, because you lost some energy to that person, and he, that person also gained some energy, he will go some other direction and you will go some other direction. Same thing happen here also. Okay, now we will discuss that one. Okay, I will share again notes, and in the notes I will. So here, see, just you have seen, observe this one. Okay. So here, first, here electrons are there, and nucleus, this nucleus and electrons revolve around the nucleus, and once photon hit here, okay, this electron moving one direction and photon also moving another direction. So this is losing some energy. The initial wavelength of the photon is lambda I, and final wavelength of photon is lambda f. Okay, lambda f minus lambda I, that is the shift in the wavelength. Or you can write shift in the wavelength means you can write shift in the energy also, you can write shift in the frequency also, you can convert anyway. Okay, that is no problem. Okay, or you can write delta lambda equal to h by m naught c into 1 minus cos theta. Here theta means scattering angle. So suppose the incident direction and how much angle it is scattered, or how much angle it is the photon is deviated after scattering, after collision. Okay, that is the theta. Okay, now we will see the experimental setup and derivation, how this expression they derived. Okay, how this expression they got, we will see this one also. Okay, so after first we will see experimental setup and experimentally how we can explain this Compton effect. Okay, see here. Okay, initially what we have a here X-ray radiation. Some to generate X-ray radiation, we have some here some filament or some tube. Here we will have some here X-ray source. Okay, this is X-ray source. X-ray source. Here there is a some slits. Okay, why you need slits? Slits to make a beam very fine focused beam. Okay, this is some slit L1 or L2, two slits. After that, we will use some target material here. Target material, any material. Suppose you want to some nickel or copper, any material you can keep here. You can hit the this here. You can keep the material, and after hitting this material, here some this photon will scatter in different direction. Scatter in different direction. Okay, we are not taking here electron, only scattered photon wavelength change in the scattered photon only we are seeing. Okay, so photon is hitting, coming and hitting the this target material. This is target material, and after hitting, after making collision, this photon will scatter in different direction. Okay, here also we have some scale, that is Bragg's scale. What is that? Bragg's scale. Okay, Bragg's scale, or you can say Bragg X-ray spectrometer also you can say. Bragg Bragg's X-ray spectrometer. Okay, X-ray spectrometer. So here you can change the angle. Okay, this is the incident path of the ray. Okay, this is incident path, right? The photon is coming. Suppose if it is not hitting any material, it will travel in this way, right? This is the incident path, this is scattered path. Okay, the lambda I, this is incident wavelength we know, incident photon wavelength we know, but final wavelength we don't know. This is we don't know. After scattering, how much wavelength is changed we don't know. Initially, suppose we are using 500 nanometer or 500 nanometer wavelength light, we hit this material. After scattering, this it is having some energy, right? Hc by lambda. Okay, this photon lost some energy to this atom or electron. After that, this energy and frequency or wavelength it will change, we don't know that one. Okay, we will use the Bragg spectrometer, and whatever scattered photons we will collect using this spectrometer. After this collection, we don't know, this ray will go this direction, or maybe this direction, or maybe this direction it will go. We don't know which angle it will scatter. Okay, we will measure the scattering angle using this spectrometer, and also we will collect all scattered X-rays or scattered photons. Okay, after collection of these photons, we will use the Bragg's condition, that is n lambda is equal to 2d sin theta. N lambda is equal to 2d sin theta. Okay, here we know theta, and here also this is the displacing. Spacing means, suppose here crystal, if you take any crystal, atoms are how crystal means what? Crystal means what? Crystal means atoms are arranged in a systematic periodic manner. That is the crystal, right? Any crystal, if you take any crystal, atoms are arranged in very systematic manner and periodic also. Okay. The d-spacing means, or atomic spacing means, the distance between two planes. If you take this one, you call it a plane, crystal plane. Okay. the distance between two crystal planes, that is the d. We know every atom we can estimate this one. Okay, this we know, and using this one we will estimate the n is the order of diffraction. Okay, first order diffraction, second order diffraction, like that. Okay, from this expression we can estimate the lambda. Okay, you can estimate the some lambda value in nanometer or angstrom, whatever. Okay, so here we are estimating the lambda of scattered photons, lambda of scattered photons. Initial shift, initial wavelength we know, and after collection of the scattered photons we are using Bragg's condition and estimating the final wavelength of photon. Okay, photon final wavelength. Okay, after that we can use the Bragg's this condition, lambda dash or lambda f minus lambda I. You can estimate the delta shift, right? Delta lambda you can estimate, or you can plot this also using this one. Okay, you can plot the graph. Sorry. So first this is the wavelength and this is the intensity. Okay, you can plot the graph intensity. Okay, here you will get the peaks, two peaks you will get. Okay, this peak correspond to incident wavelength, incident photon, and this peak correspond to scattered photon, or this is lambda I. This peak is where we are getting the maximum wavelength, that is the lambda f, and this is the lambda I. Okay, where we are getting the in this peak 1, and if you take peak 1 and peak 2, this is the lambda I incident photon wavelength, and this is the lambda f scattered photon wavelength. Okay, using you can plot the graph and you can estimate the shift, how much suppose this is initially we have this much lambda I is less. Why it is less compared to lambda f? So if you plot this one in frequency, in terms of frequency, how it look like? Suppose this is intensity and this is in terms of frequency, how it look like? Our frequency or energy. So first peak is higher intensity, right? Higher intensity. Second one is lower intensity. Why? Because lambda I is smaller for incident photon. That means frequency is high or energy also high, right? Frequency or energy high, right? And this is the lambda nu f, or you can say nu f. Are you listening? Hello?
Yes, sir.
Yes, sir.
Yes,
So
sir.
here see, after first what we will do, we'll use the X-ray source. From there we will incidence these X-rays on some graphite material or any material. After incident, this photon will lose some energy to that atom or that material. After that, these photons will scatter. These scattered photons will collect using Bragg's X-ray spectrometer. Bragg's X-ray spectrometer. After that, using Bragg's condition, Bragg's diffraction condition, we will estimate the wavelength. We will estimate the wavelength. The theta is the scattered angle. How you will estimate the scattered angle? Suppose if it is any scattering, without any scattering, this is the direct path, or it is a same path. It's initial path or original path, of photon. After scattering, it will go some different angle. It will scatter in different angle. This is the angle. This is scattering angle. We can estimate using this Bragg's spectrometer. After that, we'll collect the scattered photons and we will estimate the final wavelength of the scattered photons. We know initial photon wavelength and we know final photon wavelength. From there you can estimate how much wavelength. If you reduce final wavelength minus initial wavelength, you can know how much energy is reduced, how much frequency is reduced, or how much wavelength is increased. We can estimate how much photon energy lost in this collision process. We can estimate. That is only Compton effect. Okay, so once you collect, you can plot the graph lambda versus wavelength versus intensity. Okay, lambda I peak intensity is less and lambda f frequency, lambda f peak intensity is high, because scattered photon uh, energy is reducing, right? In the collision process, scattered photon is losing energy. So final photon energy is less compared to incident photon energy. That's why lambda is inversely proportional to the energy or inversely proportional to the frequency. So incident photon wavelength is less and final photon wavelength is high. Suppose if you plot that graph, same graph in terms of frequency or energy, incident photon frequency is high and also energy also high. So if you drop this curve in terms of frequency and energy, the first peak intensity will be high and second peak intensity will be less. Okay, using this one we can plot, we can compare how much intensity or how much energy lost in this scattering process. Okay, using scattering effect we can see incident photon, how much energy is lost in this collision process we can estimate. Okay, this is the experimental process. Okay, experimentally you can estimate the shift in the wavelength of incident photon and scattered photon. Okay, is this clear up to now? Any doubt up to
Yes.
now? If you have any
No
doubt,
doubt.
you can. If you
Sir,
have doubt, you can please ask. Okay.
sir,
Yes, please.
actually I have a doubt.
Yes, please ask.
This Prompting effect only explains scattering of X-rays or any other electromagnetic waves.
Yeah, X-rays also electromagnetic waves, right? X-rays means here stream of electrons or stream of photons. This is also kind of depending on energy. We are calling this EM waves. We are calling, suppose we have EM rays, right? EM waves or EM rays. Depending energy, we are calling X-rays or photons. This X-rays also some kind of photons only. High energy photons. That's it. Or stream of electrons also you can say. Okay,
Okay.
that yeah, the same kind only, depends on energy. We are calling X-rays or radio waves or photons. Okay, that's only. Okay, this also EM rays, also X-rays also EM rays only. Okay.
Okay. Thank you, sir.
Okay, next we will go to the theoretical derivation of this Compton shift. Okay, this is experimental procedure. Using experimental procedure also we can estimate the shift in the wavelength or energy. Shift in the how much photon is, how much photon how much energy is losing in this collision process or in this scattering process. We can estimate experimentally also. In theoretical also we can see how we can derive that expression, how we can estimate the shift or change in the wavelength. Okay. Okay. Here also see Compton derived this expression. What is that expression? Lambda f or delta lambda is equal the shift in the wavelength